manipulator is independent of any specific definition. So robotic specialists agree that robot manipulators is the most important form of industrial robots. So manipulators are nothing but it is not only about industrial robots, it is also used everywhere and it will be soon common. So as of now, we'll be concentrating only about the industrial manipulators. So it consists of the following physical components: mechanical system, sensors, and controller. So in the mechanical system, the basic components are the arm, end effector, and the actuating mechanisms. So the arm usually consists of six rigid links connected together in an open kinematic chain by revolute or prismatic joints. And it allows the robot to position the end effector in different locations in the workspace. So I hope you could understand now like what is a link and what is an open kinematic chain and what are the different types of joints, I mean the revolute and prismatic, and how the degree of freedom is working and how this arm is being used to position the end effector in the different locations in the environment, working environment. The end effectors are generally just as I said earlier, it is the tool or the end effector can be an welding torch, electromagnet, sensors, and grippers. It provides some meaning, it provides the means of manipulating objects of or performing various other tasks in the workspace. So it is basically wherever we use or whatever purpose we use inside our workspace, the end effector is going to affect it, or it is going to serve the purpose of the robot. So the actuating mechanism consists of power source, like the actuators are just I have mentioned electric actuators, hydraulic and pneumatic. And drive mechanisms are going to be the chains, gears, links, and joints. So the sensors, now coming to the sensors part. There are different types of sensors. For example, we can use an visual sensor, acoustic sensors, force sensors, and etc. So I'll talk about sensors in brief in the upcoming sessions. So just stay on with this as of now. So the sensors measure and determine the state of the manipulator links and the end effector. So state in the sense, it determines the position of the manipulator or the end effector or the orientation or even the velocity at what velocity the end effector is being moved. So those kinds of measurements are being done by the sensors. So furthermore, sensors measure and determine forces and moments exerted by the manipulator on the object of on the object. Yeah. So we could know that how much pressure is being exerted from the end effector to the object. So if you're grabbing a hand or grabbing an object, we should know that how hard we are going to hold it, or it should not damage the product or the object. So for the purposes, also sensors are being used. Finally, the controller. So the controller is a device which supervises and regulates the programmed motion. So robots are generally of three types: fully manually controlled, and semi-autonomous, and completely autonomous. So fully manually operated robots are being controlled using completely by a controller, and it is being instantaneously given commands from an human being. So semi-autonomous robots are nothing but it partially takes inputs from the human and it works autonomous also. We can stop the robot whatever the robot is being doing for a long time, and we can pause it, we can play it, we can recommend it according to our wish. And the third one would be the completely autonomous robots. So the completely autonomous robots are like totally humanoid or totally artificial intelligence being implemented in it. So we can't give inputs in between when a task is being done by an autonomous robot. So these three types are being, as I said, so the human and robot interface is being done by using an controller. So that's the purpose of the controller. It is a device which supervises and regulates the programmed motion. Okay, now let's talk about the manipulators in and from a mathematical point of view. So the study of robot manipulators includes topics such as modeling and design, robot arm kinematics, dynamics, and control. And it also consists of trajectory planning, path planning, sensors like robot vision and robot control languages, which we call as NLP, also natural language processing. And each of these topics can be studied on its own in great depth as part of the education of robotic specialist or as an application area in different aspects of engineering. So I would also wish, or I would ask you to make note of these topics. So this is how an manipulator is being created or being used in this world. So manipulators are similar to robots. So they're like other types of robots. So if you are going to create a robot, start on with building and manipulator. So building and manipulator, we should know how to design it, how to model it. And I would suggest you guys to better. I would give this as in your homework. You should know the difference between the design and modeling. So there is a huge difference between design and modeling, and learn it for yourself. So I'm just asking you to learn for better understanding, and you need to know about robot arm kinematics and dynamics, control, trajectory planning, and the great use of sensors. So that's how an robot is being built or an manipulator is being built. So, however, although each one of these topics is very important in robotics application, a deep study of manipulator kinematics and dynamics is the cornerstone of successful utilization of today's robot and those which are going to be used in the future. So about manipulators. So robot manipulator kinematics. Let's talk about it because modeling and designing is not scope of this part. I mean this session. So we will be talking more about the kinematics and the dynamics of the manipulator. So robot manipulator kinematics deals with the geometry and and the time dependent manipulator motion without consideration of force or the moment that causes a motion. So, and make note of this also, you need to know the difference between the force and moments. So there is a huge difference also because it will be those topics like force movements will be covered in your first year or second year of your undergraduate degree. So you no need to be worried about it. But basically, before going to, if the students are attending this, I mean the 10th, 11th, 12th students are attending this session, I would really ask you guys to make a note of the difference between force moments and the what's the difference between what the kinematics is all about also. So I'll cover up most of these topics in the session, so try to cope up. So in other words, they deal with the spatial configuration of the manipulator in the physical space. So that's how the kinematics is being the robot manipulator kinematics deals with. So in particular, the kinematic analysis of robot manipulators is concerned with configuration and motion analysis. So configuration analysis is nothing but it deals with the possible mathematical description of manipulators, spatial configuration as function of time. So see, actually, take a good relaxation now and just want to listen with a huge concentration because this is bit important because there's two types of analysis. So kinematics analysis is being done by two types: configuration analysis and motion analysis. So what configuration analysis means is that configuration. So if you understand the term configuration, you would understand the configuration analysis term totally, because configuration is nothing but it deals with the manipulator's position and orientation in the 3D dimension or in the real world in the function of time. Because with respect to time, the position of the manipulator or robot is being changed. So those change of movements or those change of action is called as the configuration. So configuration analysis deals with possible mathematical descriptions of manipulator spatial configuration as function of time. So I hope now you could get at or understand what configuration analysis is all about. The second thing is motion analysis under the kinematics of manipulator. So motion analysis deals with the first and second time derivatives of configuration functions. So this is a bit complicated, but try to make note of it because the dynamics of a robot deals with the relation between actuator torque or forces and the manipulator motions. So considering its mass and inertial properties, those are a few properties which are being considered in performing configuration analysis and motion analysis. So these relations define the dynamic equation, just an equation of motion of a robot manipulator, which are fundamental to any robotic application. So if you're going to learn about the kinematics of manipulator, it is being directly involved or directly applicable to other types of robots also. So now let's discuss about the basic problems in robot manipulator dynamics. So in a dynamic model, first of all, you need to understand what dynamic is. Dynamic state is nothing but any object in this 3D world which has a motion or under any kind of action, it is called as an dynamic model. So any kind of object, literally from a small eraser being thrown by you, or even the whole asteroid hit on the earth. So those kinds of motions are called as dynamic. So in dynamic model of a system, there are two main aspects with which one is concerned as a motion and forces. So these two are the basic aspects of dynamic model or dynamic model of a system. So the motion of a system is called as its trajectory and consists of a sequence with the desired positions, velocity, and accelerations of some point of the system. And forces usually characterized as internal forces and external forces. So internal forces are nothing but the constraints which we give to the robot or a manipulator, and external forces are nothing but the external external action which will be required, and those kinds of forces will be given from outside the system. So the external forces are the ones which causes the motion, and the internal forces are nothing but which constrains the motion. So in robotics, a dynamic robot model usually describes the relationship between robot motion and robot's force, which causing that motion. So that given or of those quantities, we can determine many other aspects also. So there are therefore many other problems which will be considered in the following slides. So basically, this slide is about the motion and forces. Any one of the information is given, either the motion or the force applied to a robot. We can use that information to determine the uh, other aspects, like we can know the configuration of the robot or the any other orientation of the robot in an environment. So the arm or articulated portion of a robot is usually constructed as series of coupled bodies known as links. Because I have mentioned this in the previous session also, a robot arm or a manipulator is nothing but it is a series of connection of coupled bodies or rigid bodies, which is known as links. So once you have determined the degree of freedom, you need to apply the kinematics and dynamics to give the motion of the robot. So in if every link is connected to at least two other links, the kinematics is a kinematic chain is said to be an closed chain, and such mechanism is called as a linkages. So the second problem in the last session is an example of the linkages. It is a closed system and there isn't any kind of prismatic linkages, only revolute joints with only revolute joint with it. And I hope you could remember that. And that's how the closed chain looks, and it is called as a linkages. Okay, so however, since a kinematic and dynamic analysis of closed kinematic chain is involved, most industrial robots have open kinematics chain only, and that's what manipulator is about. So manipulators are nothing but it is of completely open chain. So with some form of end effector attached to the final link. So depending on the intended application, the end effectors are being used. And so we usually refer to this class of industrial robots as the robot manipulators. So the forward or direct dynamics problem, which we called as which we also call as FOP. So the thing is about the forward dynamics problem or the forward dynamics is that it deals or it is one way the force which act on a robo or given and we wish to solve the resulting motion. As we spoke earlier about the motion and the forces applied on a robot, so here comes how we are going to solve it. So forward dynamics is nothing but if we are given an robot or if we have given a manipulator and the provided informations about the robot is nothing but only the forces are given, and we need to determine what kind of motion the robot is going to perform, and that's what called as forward dynamics. The force is being given and we are going to determine the resulting action or resulting motion. So the most importance of the forward dynamics in robotics stems mainly from its use in the simulation. Simulation of robot motion is way of testing control strategies or manipulated design prior to the expensive task of working with the actual manipulator. So this is nothing but uh, using a simulator really helps a lot by constraining the cost of building a manipulator. We can't risk the manipulator being it can damage itself or it can damage the other users in or the other controllers which control the manipulator. So that's why the simulation or the simulator is being used, and robot forward dynamics in robotics is vastly used in the simulations because we can give what kind of forces and whatever kinds of constraints to a robot, and we can see in the simulation in what direction the robot is being moved or being held up. So we will also have a simulation session at the end of this course, and that will be far more clear, self-explanatory to you when you work on a simulation. So when you are doing a simulation, you will be giving the forces, now the amount of forces, and you will be watching the direction of the motion of a robot. And now I hope now you could understand what the inverse dynamics is all about. So the inverse dynamics problem is one in which we need to determine the generalized force that will produce a specified motion trajectory. So in inverse dynamics, it is very important in practical robot application because it enables us to determine the profile of generalized forces necessary to achieve a desired robot trajectory. And the inverse dynamics also plays a vital role in many advanced robot control strategies, where the inverse dynamics are used in the feed forward and feedback paths, and we need to compute online. So moreover, to ensure convergence of the control scheme, the inverse dynamics computations may have to be performed very frequently. So consequently, the formulation and the evaluation of these equations of motion affect the servo rate of the robot controller and partially determine the feasibility of implementing many controller schemes online. So basically, inverse dynamics is nothing but we are giving a motion and we are going to determine how much force would be needed to achieve that motion specifically. So this is vastly implemented in real life because in real life we could control manually the manipulator or the robot. Like we can move it along the path, whatever path we need, and we can determine what motion. I mean, the what kind of force is needed to achieve that kind of motion. So that's all about the inverse dynamics. Now, a kinematic path. So what is a kinematic pair? It is the coupling of two adjacent links. So any links is being attached to each other, it is called as an kinematic pair. In current industrial manipulators, the most frequently encountered kinematics pair and then the most simplest one are the revolute pair. It has an revolute joint and a couple of links are being attached to that revolute joint in different directions. It allows only relative rotational motion about single axis and prismatic joint and prismatic pair, which is also another common application or common kinematic pair, which allows only relative translational motion in a single axis. So for these kinematics pair, since motion is allowed in only single direction, one parameter or one variable is sufficient for specifying the relative motion between two adjacent links. This implies that revolute or prismatic pair have characterized by 1 degree of freedom. The corresponding variables which measures the linear and or rotational relative motion of kinematic pair is referred to as it is called as a generalized coordinate of kinematic pair or joint. So this explains nothing but the what is a kinematic pair and how to determine its location and its motion using the two aspects of dynamics, the motion and force. So we can use motion and force to determine the position or orientation of the kinematic pair. Okay, now let's see about few kinematic configurations which are being used in many industrial manipulators. What is a kinematic configuration? The first part. I hope you could remember in the first few slides I explained what configuration is all about. Now in detail we'll look into it. So kinematic configuration. Once the required number of degree of freedom has been decided upon a particular configuration of a joint, it must be chosen to realize those freedoms. Like for serial kinematic linkages, the number of joints equals to the required number of degree of freedom. So it is nothing but the whatever kinematic linkages or whatever series or how big the kinematic linkages can be, that that doesn't matter, but only we are going to determine the degree of freedom based upon number of joints. So it is directly proportional to each other. So most manipulators are designed so that the last n minus 3 joints orient the end effector and have axes that intersect at bridge point. And the first three joints position on this bridge point is bit important. So the manipulators with this design could be said to be composed of positioning structure followed by an orientation structure, or I can call it as a bridge. So the positioning structure is almost without exception designed to be kinematically simple. It has it will be having link twist the equal to 0 to 90 degree, and it has many of the link lengths and offsets equal to the 0. So it also have become customary to classify manipulators of bridge past bridge partitioned kinematically simple class according to the design of their first three joints. The following slides will be briefly discussing about the different types of industrial manipulators or the different or the most common of those classifications which I mentioned earlier. So looking into Cartesian manipulator, it has a most straightforward configuration because as you could see in the figure, joint 1 through 3 are prismatic. Okay, I am sorry you could not see the numberings over there. Okay, so in the side view, you could see an horizontal link, which is from the point D2 and D3. So that's the line or that's the linkage which is prismatic. And it is mutually orthogonal with an vertical link. So it can go up and down, and it can also move from the x-axis in the x direction, or the horizontal moves along the x direction, and the vertical linkages move towards the y direction, and that's called as a mutually orthogonal. So, and it is also correspondent to XYZ Cartesian directions. So the inverse kinematic solution for this configuration is trivial, because this configuration produces robots with very strict structure. As the consequence, very large robots can be built using this. So these large robots, often called as an gantry robots, so it resembles overhead gantry cranes, and gantry robots sometimes manipulate entire automobiles or inspect entire aircraft also. So the other advantages of Cartesian manipulators is that the fact that it has the first three joints are decoupled. This makes them simpler to design and prevents kinematic singularities due to the first three joints. So the three joints provide the motion, but it is kind of useless when it comes for an dynamic analysis. So their primary disadvantage is that it is that all of the feeders and fixtures associated with the application must lie inside the robot configuration or the robot's environment. So consequently, applications work cells for Cartesian robots become very mission dependent, because carrying a huge car or something which weighs tons and tons can be used under gantry robots, but it also need under a complete human controlled, and it can be dangerous at many times. You could see the GIF image, and that's how an articulated robot looks. And I hope you could remember the articulated robot GIF in the past. So sometimes it is called as an adjointed robot, or it is it is called as an anthropomorphic manipulator. So you don't need to be worried about those terms. You should just remember how it works. So a manipulator of this kind typically consists of two shoulder joints, one for rotation about the vertical axis and one for elevation out of horizontal plane. As you could see in the image, one link is being forced out or moved out from the horizontal plane. And another is the function is nothing but to rotate in certain axis or whatever desired axis that we provide them. An elbow joint, you could see an elbow joint which whose axis is usually parallel to the shoulder elevation joint, and that's the elbow part. And two or three wrist joints at the end of the manipulator is can be used. So few examples are the Puma 560 and Motoman L3. So these two are examples of an articulated robot arm. So the image which, I mean the GIF which I have provided in the slide is the example of Puma 560 model. So articulated robots minimize the intrusion of the manipulator structure into the workspace, making them capable of reaching into any kind of confined space. They require much less of overall structure than Cartesian robots, making them, which makes them less expensive, and for it also does not constrain a huge space. Spherical configuration, which you could see in the image, it has many similarities to the articulated manipulator. But with the elbow joint replaced by a prismatic joint is the only difference. This design is better suited to some applications than in an elbow design. So the link that moves prismatically might telescope or even stick out of the back when retracted. So I'm really sorry I could not provide you a video or GIF image of spherical robot. I mean a spherical configurator manipulator. And if you wanted or if you're interested, kindly YouTube it for how an spherical manipulator works. The cylindrical manipulators. So it consists of prismatic joint for translating the arm vertically, and the revolute joint with a vertical axis and another prismatic joint orthogonal to revolute joint axis, and finally a wrist of some sort. So the main difference between the cylindrical and an gantry robot is that the cylindrical manipulator has much more degree of freedom because it consists it can translate the arm vertically, and the revolute joint is being attached for the vertical motion, and another prismatic joint is also being used for orthogonally to revolute the joint axis.